A balanced power system. Introduction to the balanced set of phasors. Module 1. Introduction to the balanced set of phasors. In this module, we're going to talk about a very important concept called a balanced system, or a balanced set of phasors, which is widely used in many areas of the power system. Be sure to check out the resources section in this video for helpful comments, suggestions, and clarifications. When thinking about transformers, transformer connections, generators, the square root of 3, symmetrical components, and many other things about the power system, we often assume that we're operating in a balanced condition, or we have a balanced system, or we're operating in a normal or steady state condition, or we have a balanced set of voltages or currents. All these points imply one thing: a balanced system. A balanced system is simply a set of phasors, and it could be voltages or currents, that follow 3 rules at all times. These 3 rules are: rule number 1, phase A, B, and C voltages or currents must have equal magnitudes. Or in other words, phase A voltage must equal phase B voltage, and phase B voltage must equal phase C voltage. All 3 phasors must have equal magnitude value. Rule number 2. Phase A, B, and C voltages or currents must be equally displaced. Equal displacement between 3 phasors in a 360-degree circle implies 120 degrees displacement between all 3 phasors. This will become very clear with an example later in this module. Rule number 3. Phase A, B, and C voltages or currents must have either an ABC or ACB phase rotation or phase sequence, and must rotate in a counterclockwise direction. We'll explain ABC or ACB phase rotation or phase sequence in just a little while, but the most important thing to remember about rule number 3 is that all 3 phasors must always rotate in a counterclockwise direction as per the IEEE and ANSI standards. All 3 rules contribute to something we call a balanced system. So let's illustrate an example and see if we follow all 3 rules. We're going to draw a phasor diagram with an x-axis, y-axis, and a nice round circle right in the middle. And we're going to label degree marks at every 30-degree increments. We'll also draw a different colored line at the 0-degree mark. This is our reference line. Okay, so first we'll draw a phasor which we'll call phase A voltage. When thinking about a phasor, the magnitude and angle of that phasor should be very apparent. So suppose phase A voltage equals 2400 volts at 0 degrees. We'll represent phase A voltage by drawing a line starting at the origin and ending at the 0-degree mark. So the actual length of this phasor represents the magnitude of phase A voltage. And we're assuming that the magnitude of phase A voltage equals 2400 volts. So in other words, the length of the phasor represents 2400 volts. The angle of this phasor is represented by the angle between the reference line and the phasor. Since the phasor overlaps the reference line, or is in phase with the reference line, we understand that there is 0 degrees between the phasor and the reference line. So mathematically, we'll represent this phasor as phase A voltage equals 2400 volts at 0 degrees. Next, we'll draw another phasor and call it phase B voltage. We'll assume that phase B voltage equals 2400 volts at 240 degrees. We'll illustrate phase B voltage by drawing a line from the origin towards the 240-degree mark. The magnitude of phase B voltage is 2400 volts, which is represented by the length of the phasor. The angle of the phasor is represented by the angle between the reference line and phase B voltage. So we'll begin at the reference line and rotate in a counterclockwise direction until we get to the phasor. The angle between the reference line and the phasor is 240 degrees. Mathematically, we represent this phasor as phase B voltage equals 2400 volts at 240 degrees. We'll draw the last phasor and call it phase C voltage. We'll assume that the phase C voltage equals 2400 volts at 120 degrees. So for phase C voltage, we're going to start at the origin, draw a line toward the 120 degree mark and stop here. The magnitude of phase C voltage is 2400 volts, and the angle between the reference line and phase C voltage in the counterclockwise direction is 120 degrees. So mathematically, we'll represent this phasor as phase C voltage equals 2400 volts at 120 degrees. This, my friend, is what we call a balanced set of phasors, which contribute to something that we call a balanced system. In the next module, we'll continue this example and make sure that we're following all three rules. This module was brought to you by GeneralPack.com, a platform to ask, learn, share, and grow in the power system protection, automation, and controls industry.